In this video, I want to show you a cool application of matrix multiplication. Matrix multiplication can be used to transform geometric objects. For example, say I have this row matrix and this square matrix. Let's multiply them together. I'll get 1 and minus 3. Okay, so what's the big deal there? Well, if I think about that first vector, right? Or excuse me, this first matrix, that row matrix, I could think about that as telling me about the point 1, 3, or maybe even as thinking of a vector 1, 3, right? I multiply it by a matrix and I get out this other row matrix, 1 minus 3, which I could think about as this point or a vector pointing to that point. So I've transformed the original point to that one. It's literally turned. Every matrix multiplication can be thought of that way. So let's look at a more interesting example. Let's imagine I wanted to transform this red square, right, this 1 by 1 square in the first quadrant, by multiplying every point on that red square by this matrix. A little more interesting than the last one. Well, if I look at this square, I can think about the ordered pairs of the points around it. And I'll definitely include the corners here in my calculation. And maybe a few other points just to make sure I'm getting everything absolutely correct. So let's start with the origin. I'm going to take the origin, I'm going to multiply it by this matrix and see what happens. So think of the origin as a row matrix. Multiply by 1 minus 2, 1, 2. And I get out the origin. Not a very interesting transformation on the origin. This red dot gets moved nowhere to that purple dot. Let's see what happens when I get to this corner. The point 0, 1 becomes the point 1, 2. All right, well, that's at least a little more interesting. That's this point up here. Now, I would like to imagine what happens with all of the points on this side of my original square. And my guess would be is that all of the points from the square still connect to their two endpoints. But let's make sure. Let's not just take my word for it. Let's try one more point that would be on that side. Let's let that be the point 0, 1/2. So I think about 0, 1/2 times my matrix. And let's see, I would get 1/2, 1. Well, 1/2, 1 is that point right there that does nicely fall right between these two. So I do think that whole side gets mapped to this whole side. All right, well, let's move on to the next corner. All right, so 1, 1 times my matrix will give me 2, 0. So this corner gets moved to this point right here. And again, I could think about all of the points in between. In fact, why don't you pause the video and make sure that this point gets moved exactly where it's supposed to go right there. So pause the video and do that much. All right, you should have found that that point does lie right on the midpoint of that side I drew. And what I'd like to do now is go on and move my final corner. And I find out that point will go to the point 1 minus 2. Let's see, 1 minus 2. So my original square looks like it got turned and stretched, right? So it got translated, right, and then also scaled differently. And so let's think about that part. There was a rotation, right? It turned, but it also seems to have been stretched. My original square certainly had an area of 1. I applied my matrix, and I get this diamond, and I want to think about its area. Well, if I just look at a quarter of it, I get a triangle. And that triangle is a 1 by 2, right? So base by height, and right, so 1/2 base times height, I'd get an area of 1 just for that part. So 1, 2, 3, 4. So I was stretched by a factor of 4. Or scaled by a factor of 4. Cool. So this matrix turned my original square and stretched it. I want to talk about this stretching and a way to know that, a way that I knew when I started that this matrix would actually stretch my original square. The determinant of a 2 by 2 matrix So I could write that down as determinant, and then in there write a 2 by 2. And I'll just use A, B, C, and D as the entries. Or instead of matrix brackets, we replace them with a determinant symbol, which looks a lot like absolute value. The definition of the determinant of a 2 by 2 is this calculation. AD minus B times C. You multiply the diagonals, and it's this diagonal minus that diagonal. That's how you compute the determinant of a 2 by 2 matrix. And so if I look at our matrix and I go to calculate its determinant, I get 2 minus, and negative 2 is 4. That's my scaling factor, right? This idea of determinant tells me the scaling factor of that 2 by 2 matrix. Now, what's cool about that is there are matrices that do all kinds of rotations and turns, even flips. And so if I have a matrix that turns, my determinant will be 1. I didn't stretch it all. And then I could imagine something that took this square and made it bigger. Well, like this one did, right, by a factor of 4. So let's say I had a small square that looked like this, right, with a green corner, a blue corner, a red corner, and a purple corner. And then I apply a matrix that makes it bigger like this one, turns it, but also flips it over. All right, well, the rotation, that's just about some of the quantities in the matrix. The stretching would be the determinant, but since it flipped over, my determinant would be negative. And that's a really cool thing. Now, one of the fun things is if I flip twice, my determinant becomes positive again, right? Because the opposite of an opposite. All right, so simple definition for a 2 by 2 matrix. In the next video, I want to talk about the determinant of a 3 by 3 matrix and hopefully use that to talk about the cross product.